Welcome to another problem session. So we have a really interesting problem today. Um, it's a it's this is a heavy rope. So let's see this black one. This is a rope. It's supposed to be straight, and it's got some mass M, length capital L. And it's swirling at a constant omega and keeping this angle fixed. So this is fixed, okay? And it's going around, so you can see it's going to make a circle like this, okay? And so it's going to have tension. But this tension will actually vary from place to place. Like, if I'm just outside the rope here, just immediately outside at that point over there, of course, the tension is zero. Just if I go L and a little bit more, the tension is zero. So I'm not saying the tension is zero in the rope, but I'm saying just outside. Of course, the rope doesn't exist, so the tension will be zero. Okay. And the question is, what is the tension at distance at this point of the rope? So this point is marked, but there's nothing, not anything there. It's just a point on the rope. All right. So basically, tension is supposed to be a function of R. R is along the rope. Okay, so how do we handle this kind of thing? It's pretty, if you don't know the techniques of infinitesimal elements and how to look at the F equals ma on that element, you're going to be lost on this. So when you look at F equals to ma, this m can be anything, it can be part of the body, and then you just look at all things. So if you look at a small piece, and you can call it like a delta m or dm. Sometimes people use this delta m, sometimes call it dm, sometimes call it delta m. So these are kind of small pieces. Okay, and so we can see. Let's look at a very small piece here. So they all indicate infinitesimal, and I kind of prefer this. I'm not taking a derivative or anything yet. Okay, it's just that it's infinitesimal. These guys also infinitesimal, but this one I'm more familiar with the notation. So I look at a small piece. I'm going to call it dm, and so the equation I want to write is f on that dm equals to that dm times acceleration of dm. So that's the equation. This becomes that equation. So I need to just figure out f and things like that. So of course you look at it, well, there will be a gravity pulling it down. That's going to be dm times g. And it has two parts. Even it's infinitesimal, it's got a part at, this is the piece I'm looking at. So there's a tension pulling that way, and there's a tension pulling that way. So this tension I'm going to call R plus dr, or you can write a T at R plus dr, however you want to do it, okay? And T at R, you can write T. This R is just a label here, okay? This R looks like a function. It's fine because we're looking at distance measuring from there along the rope. So these are two. So let's call it. So there's a tension that way, and there's a tension that way. The opposite direction. but there are two of them, and there's nothing else applying force on it. So this side got done. So we know these are the forces, and then there's gravity down like that. And we know this angle happens to be theta from this angle over there. So these all of this nicely done. Okay, so now how about this guy? This one we already know. What is the dm? Well, we could measure along this piece, size of the piece, because we want along r. Let's call this size dr. Okay, so this will be equals to size of that guy. Well, it says you have a mass m, length l, and they're uniformly distributed over there, right? So how much mass will be? dm will be mass over length. That's the linear mass density times dr. So we got that one too. How about acceleration part? What is the acceleration of this thing? Well, you just have a look at the motion. It's going its own circle, a smaller circle than that, and it has a radius this r. And if this is r, and let's call this radius capital R, so this capital R is going to be r sine theta. I think so. Yeah, so this is going in this circle. So it's a circular motion. So if I look at something circular motion, looking from the top, and it's going that way to the center, there is going, so the acceleration will be towards the center. So the acceleration will be like that, and its magnitude will be v square over capital R. This was R. So what's the v? If it's going in omega and it's going in the circle of radius capital R, so this will be omega times capital R square over R. So this omega square R. I like to remember this formula for centripetal acceleration, so I don't have to do this every single time. You know, people remember that formula all the time, but this is equally, useful to remember. So we know, but we don't. We have to make sure it's a vector thing, right? So let's see. We are going to have to implement this. So in this picture, it looks like it's going at this way. This what its acceleration looks like, and has a magnitude this. So at this instant t, vectors are all in this plane. So you can say we're talking about this plane. All the vectors are in this plane. Okay, and so I'm free to choose any coordinate I like. So usually it helps to have acceleration along one coordinate. So we can choose like x this way and y that way. So we can write x equation of motion, and then we can write y equation of motion. Maybe both are useful, maybe one of them useful. Let's try x equation of motion. So to break it down like this, every vector is coming from that same place, x and y, or same orientation as that. So tension, if this is theta, then that's theta. So this is going to be positive, and this is going to be negative, right? Along the y-axis. Along the x-axis is going to be this. This will have positive, and this will have negative. So t at r plus dr, and if this is theta, then this is going to be sine theta, and the other guy will be minus t at r sine theta, and it's going to be this guy doesn't play any role in the y-axis for this, x-axis for this, so and this is going to be delta m times omega square r. R is this omega square. Let's do a little bit more massaging. My delta m is going to be a little small. That was this guy. So m over L times dr omega square. This big R was r sine theta. So it turns out the sine theta is kind of canceling out from all this thing. And so without looking at this, just x looks like is enough. 3r plus dr minus dr. I can take dr, put on this side, and then I get a minus m omega square m omega square L r okay. So we get a now with, let's see if we do limit dr goes to 0, so we get to a point, and all this point things went away, just everything is very nice. So this is just turns into dt dr equals minus m omega square over L r. Well, it's kind of like it is a differential equation, and we need to solve it, right? So here separation of variables will help. So let's separate the variables. So we have a dt on one side minus mx squared over L. So rather than keep writing everywhere, let's just call this blob, which doesn't depend on t or r, this blob, let's call it b for the blob. So minus b r dr. Okay. Now you need to integrate, and this is constant, so integrate. In order to see the relationship, I have to integrate from, say, r equal to 0 to r equal to 0 to arbitrary r, and this is just this is a dummy variable when you integrate. So you want to call it dummy variable, it's fine. This is the variable I want to go to that point. But r equal to 0, I don't know what the tension is at r equal to 0. So t at 0, and this is the t at r I need to know. This is what I want. So this integration will give me that. And so when I do this, I get t at r minus t at 0 equals minus b over 2 r prime square 0 to r minus b over 2 r square. Okay. Okay, so but we need to figure this guy out. How do we figure that guy out? Well, remember originally in the beginning I was saying that if this is an honest function and this is all the way to L, then if I take a limit L from this way or that way, and so this was the derivative, so this derivative probably goes all the way to the end, right? So this derivative, it didn't say can stop at some place when we are deriving this. So if this is true also at t equals to L, then this thing to exist at limit, R equals to L, then R, if I take L plus, I go limit from this side to get to the end, must be same as that. So if I were to take a limit R coming from L plus, this should be okay, right? Well, when we go L plus, there's no rope there, so no tension, right? So this is going to be TL L plus, and so this is going to be 0, and this has no R there, so T at 0, and this is going to be minus B over 2 L square. I mean, coming from above, coming below, this R square is going to give you L square. So T0 is simply B over 2 L square. So I can now put this back in there, and T at R is going to be B over 2 L square for this term minus B over 2 R square. So basically B over 2 L square minus R square. So, if I plot, this is R and this is L and this is 0. So tension is going to be some T at 0. So this is T of R. T, how tension is going to vary, is going to go to 0. And it's going quadratic. So I think it's going to come, initially doesn't, slope is very low, but it goes like that, square. So it's going to go, and of course after that tension is going to be all 0 because no rope here. So this formula is R less than equal to 0, less than equal to 1. So that's the form. All right, this is actually a very good techniques to master. There are a whole bunch of things here I covered. One is how to really nail down this small element and how to look at forces on two sides, and then discover a plane in which set up the equation of motion. Okay. These techniques are in Feldspar very important, and probably you have seen this. For example, when you have a column of air, okay, so this is air, and it gets thins out as you go. This is ground, so if you go z-axis, at some point the air would be, there'll be no more air, right? So what's the pressure over at some point z? How do you find pressure? Well, you can take, so we want to know pressure over here at this height, so z equal to 0. How do you know that? Well, you can take a small element, okay, and so this is the delta m, and acceleration is 0 now. So the forces will have to be constant here, right? So on top, pressure z plus dz. On the bottom, pressure is at z. So this is z, and this is z plus dz. This height is z, this height is z plus dz. So those are the only forces. So the weight, as this pressure is going to apply, and this area of cross section, say, let's call it delta A above, and below is same delta A below. So pressure T plus delta Z dz delta A, that's the force from above, that's the minus, plus force from below is pointing up. P at, this was Z, and this is Z times delta A. So these are two forces, and plus its weight, delta mg is minus delta m g, that's the weight, and that's delta m times 0 for acceleration. It's acceleration 0. So this all balanced out. So what's delta m? So delta m will be whatever the density of air at this height, at height z, whatever the density is here times the volume of this thing. Volume is delta A times dz. So this equation, you can see over here, it actually tells, models atmospheric pressure very well. You can plug in there, and you got, let's call it rho z delta A dz, and make it equal because there's 0. Delta A cancel out from each term. So minus P z plus delta z minus Pz, I mean dz equal to rho g dz. And you can take this minus put on the other side. So this is dp dz equals to minus rho z g dz. So the exactly same type of problem. It all depends on now what the density is going to be like. Your model of density, okay? So suppose density is, an example will be like, I got a density goes as, whatever the densities over here, rho at ground level, maybe it goes as e to the power minus z over some big height, you know. So it eventually goes to 0 as z goes to infinity. So this is model, and h is like a 40 miles, whatever, 50 miles, some h is very large number. So this is, let's call it S0. This is not to do with this height. It just, so this is known, and this is known, and maybe this function is just a modeling with the, I'm not claiming that this is correct, okay? This model may be correct, incorrect, but how do you handle this kind of thing? So you can get a dp equals minus g rho 0 e to minus z over h0 dc. So that's what we're going to get. So now I'll have to integrate this guy, this constant, integrate p at ground level, p at the ground level 0, p0, and p at the height z. Okay, we can call it like that, or just like that. And z at 0 to z, and this is just a dummy index now. So we just have to integrate this, and you can, in this model, you can tell what the pressure looks like. So p at height minus p at ground level will be equal to minus g rho 0, and this is going to be, if you have a e to the power ax dx, so this should be e to the power ax over a, right? You can take a derivative of this, you can get that. So it's going to be 1 over minus 1 over h0 is minus z prime over h0, and I have to do this. So this minus becomes plus, and So G rho 0 H0, this guy evaluated Z is e to the power minus Z over H0. Evaluate 0 becomes a minus 1. Of course, 1 will be more than that, so you should write it. P of Z is P of 0 minus this thing G rho 0 H0 1 minus e to the minus Z over H0. So that's going to be answer for atmospheric pressure at that height if the atmospheric density in air is varies with that model. Maybe another model, it will be a little different expression. But the actual formula is not important. What's important is what I did, okay? What I did over here and how I took infinitesimal element ideas and just F equals ma. All it was F equals ma here for that infinitesimal element, and actually walked through a reasonable steps, right? And eventually I got a useful thing that I can go and test in the lab or experiment and observe it. Okay. All right, so this is it. If you like this kind of explanations and things like that, tell your friends, tell friends that it's a good website or good things, and of course subscribe. It helps the channel grow. I'm not going to put ad, etc. if you're worried about that. Or you can check out my website, physicsbootcamp.org. Okay, enough advertisement. Take care. Bye.